Hello students, in this video we'll talk about shortest path problem and it will be using Dijkstra algorithm. So what is shortest path problem? So if you have any graph in which the edges are assigned certain weights and we have to reach from one edge to another edge, then the smallest way which we choose, it's the shortest path or the shortest path problem. So it has many application in our real life. Shortest path problem is also used in Google Maps. When you enter a location, you want to reach a particular location, Google Maps always shows you the shortest distance. It is using Dijkstra algorithm over there. It is also used in IP routing to find the shortest path. Okay, so if it is also used in telephone networks. If you want to send a signal, then the receiver should receive the signal as early as possible, so it will choose the shortest path. So it's using Dijkstra algorithm over there. So let's see how to use Dijkstra algorithm on this question. We have this graph. Okay, there are 7 vertices here, A, B, C, D, E, F and Z. 7 vertices are there and each edge is assigned some weight. Okay, each edge is assigned some weight. We have to find the shortest path between A to Z. I want to see how I can reach from A to Z in shortest path. So how we'll find this? You firstly have to write the vertices. We represent the vertices, so write all the vertices in this way. Okay, and then we'll choose the first vertex. We have to find the path from A and Z, so we'll choose our first vertex to be A. So A is our first vertex. Now we'll find out the distance of A from all other vertices. Distance of A from A is 0, so it is 0 here. This subscript represent that the distance of A from A is 0. The subscript is the source distance or the distance from which we are measuring it. Okay, so distance from A is from A to A is 0. Distance of A from B, from here you can see, from the graph you can see, distance of A from B is 2, so it is 2A. Then distance of C from A, distance of C from A is 1, so I have written 1A. Distance of D from A is 4, so I have written 4A. Distance of E, so it's not possible to directly reach E from A, so initially we'll choose it to be infinity. Similarly for F also we'll choose infinity, and similarly for Z also we'll choose infinity. Now I have taken a different color for this one because I have taken vertex A already in our path, in our shortest path. I have chosen the vertex A already a part of our shortest path, so that's why I have taken a different color over here. Now among all these distances, what is the minimum distance? This is the minimum distance, 1. So we'll choose in our path, we'll choose C as our next vertex. So we'll choose the vertex C as our next vertex. Now we'll see the distance of all the vertices from C. So this is already there in our path, so we'll write it as it is, A0A as it is. Okay, and we have choose the second vertex to be C, so we'll write 1A as it is. Next we have to see the distance of B from C. Distance of B from C is 2 and the path is coming from A, so 1 plus 2 becomes 3. So it's not good to write 3 here because that increases our path. Okay, so it will remain 2A here, will not change it, it will remain 2A here. Next we'll see for D. For D you can see from C to D it's 2. Okay, so 2 plus 1 is 3, so it's good. 3 is less than 4, so we can write 3 here, and the subscript will be C because it's coming from C. Then what about E? Distance of E from C is 5. So 5 plus 1, 6. So again an improvement. So we'll write 6C here. Then what about F? It's 7. So 7 plus 1 is 8. Again an improvement. So we'll write it here. Z is not reachable directly from C. So it will remain infinity. Now what's the minimum distance? Here now what's the minimum distance? This is 2 is the minimum distance. So we'll include vertex B in our shortest path. So include B in our shortest path. Write these two as it is, 0 and 1 as it is, because they are already in the path. Okay, and we have included 2A also, so we'll write 2 also as it is. Now we have to see the distance of B from all other vertices. So distance of vertex D from B, we cannot reach D directly, so we'll write it as it is, 3C as it is. Then what about E? E. Distance of B from E is 3, so 3 plus 2 is 5. So there's improvement, so we'll write 5B here. Okay, then what about F? F is not reachable directly from B, so we'll write 8C as it is. And Z is also not reachable directly from B, so we'll write infinity A as it is. Now what is the minimum among these? 3 is minimum, right? So we include vertex D in our shortest path. So vertex D is included here. Now these three things will all already in our path, so we'll write them as it is. Okay, and D is also included, so I will write 3 distance of D from D3 as it is. Now see the distance of vertex E from D. E is not directly reachable from D, so 5B remain as it is. Now what about F? F is distance of F from D is 4. 4 plus 7. 4 plus 3 is 7. So there is improvement. 7 is less than 8. So we'll write 7D here. And what about Z? Z is not directly reachable from D. So infinity A will remain as it is. Now what is the minimum distance here? The minimum is E. So we'll include vertex E in our shortest path. Now what is the distance of we'll write these 5 distances as it is because they are included in our shortest path. Now what is the distance of F from E? F is not directly reachable from E, so we'll write 7D as it is. And what about Z? Distance of E from Z is 1. So 1 plus 5. 1 plus 5 is 6. So there's improvement. So we'll write 6E here. 6E. Then what is the minimum now? Z. So we'll include Z in our shortest path. So we'll write Z here. We'll write all these distances as it is, and we'll write 6E as it is. Now we have to see the distance of F from Z. Distance of F from Z is 3. 3 plus 6 is 9. So 9Z. So we'll write 9Z here. So we'll do it for n minus 1 vertices. So here there are 7 vertices. So up when 6 vertices are included in our shortest path, we'll stop. Okay, so n is 7, so n minus 1, 6 vertices are being included in our path. Okay, now if we have to look for the distance between A and Z, what do we have to do? Length of the distance between A and Z will be 6 because we started from A and we ended up at Z. Okay, so distance between A and Z is 6. It is given here. So we'll backtrack how to reach A from Z. From Z, firstly, we are backtracking it. From Z, the path follows from E. From E, it goes to B, and from B, it goes to A. So it's like from, so it is from Z to E, then Z to E, then E to B, and then B to A. So the path is like A to B, B to E, and E to Z. So it is of distance 6. So path from A to Z is A to B, B to E, and E to Z of length 6. Okay. If you want to find distance of any vertex in this graph from A, you can find the distance from this table. Distance of Z from A, we can see it from here, right? From Z you go to E. We are backtracking. Z to E, then E to B, then B to A. If you want to know the distance, shortest distance of vertex F from A, then how it goes? From F to Z, then from Z to E, then from E to B, and then from B to A. So it goes like this: F, Z, E, B, A. So it's the distance, the path is A to B, B to E, E to Z, and Z to F. If you want to know the shortest path from A to E, it is here. You go from E to B, and then from B to A. It is of distance 5. Okay. Similarly, you can find for D, C, B, and all the vertices. So I hope you have understood this. Thanks for watching this video. Have a good day. Thank you.